you, Timo. Thank you, Timo, for the introduction, and yeah, for having me here. And I guess I am the nearest neighbor in the approximation tool around. So, okay. So I'm going to share a little bit with you of work that we've been doing with my former PhD student who already finished and moved on. Unfortunately, have left academia, but apparently you can't have them all. And so it is about stochastic solution, stochastic methods for solution of inverse problems with acoustic forward model. So that is okay. Let me I don't know who is the audience, unfortunately, so I cannot really say how much introduction is needed. So let me bear with me for a short introduction about the photoacoustic. Okay, if I can move my slides forward. Yeah. About the photoacoustic problem, that is the inverse problem that we are going to look at in detail today. So in photoacoustic, we have a very nice combination of optical contrast and acoustic or ultrasound resolution, and this is achieved by means of nature, really, because we use the so-called photoacoustic effect. So what we do, we illuminate the tissue with the short pulse of near-infrared in the near-infrared spectrum of light. So this light is propagating through the tissue, and as we are not transparent, so this propagation is kind of limited in depth and diffusive. So this gives us a distribution essentially of the photons in the tissue, you know, to a depth of about 1 to maximally maybe 2-3 centimeters. And these photons are now being absorbed, and the absorption is proportional to the absorption coefficient of the tissue. So you have this distribution that came from the diffusive illumination, and then you have this absorption that is kind of proportional to the tissue properties. So once this energy is, I should say that the optical contrast is clinically relevant, because essentially it gives us the difference between the oxygenated and disoxygenated hemoglobin. So this is an interesting contrast, and that's why photoacoustic have been gaining in popularity over recent decades, really. So once this energy is absorbed, it heats up the tissue, and then we get thermic expansion, and this finally gets released in a form of the ultrasonic wave. And okay, this, as any physical process, this conversion between the energy, the heat, and the initial pressure has some efficiency constant that we don't have a very good handle on, so we are just going to neglect it from now on. And so essentially the absorbed energy constitutes our initial pressure. And this is the initial condition for our wave equation that describes the propagation of the waves through the domain, and in this case to the boundary of the tissue where the sensors are. Okay, so with this in mind, so my forward operator is adequately described by the wave equation, scalar wave equation, with the initial conditions of this type, where this initial pressure is sitting here. Can you see my pointer? Okay, I assume that you can. So the initial pressure is sitting in this initial condition here. And so we have this, when we solve this wave equation and record the data on the boundary of the tissue over the time, this is our photoacoustic data. So this is time series on the series of sensors that are placed around the boundary. So our forward operator essentially maps from the initial pressure here to this data here, and this is of course achieved by solving the initial value problem and recording the data on the boundary. So this process we formulate as a forward operator, we are using smooth spaces compactly supported in RD, and they are being mapped to the also smooth functions in time on a set of point detectors distributed around the boundary. So this is what it is trying to convey. And so what is for the technical reasons, we need that the function on this time interval is smooth, which is enforced by this smooth aperture function. Okay, so we have a forward operator. So now what is the adjoint operator to this forward operator is essentially going backwards from the data to the domain. It's not the inverse operator though. And so it turns out that the adjoint to the forward problem is is also a scalar wave equation, but now the initial conditions are uniformly 0, and we have a source term here on the right hand side, and this source term is composed from the recorded data with the smooth aperture applied to it, reversed in time and played backwards at the sensor locations on the boundary. So, so how we go? So to execute the adjoint, we have to solve this equation and evaluate the solution at the time t. Capital T, which is the time that we kind of consider that the wave has left from the compactly supported object, the wave has left the domain. Okay, so there is also a notion of inverse operator in photoacoustics. So this is if you have a complete data and then there are all sorts of conditions and assumptions on smoothness and the benign behavior of the speed of sound, we can essentially reverse the data that we measured at the boundary and refocus them back to refocus the initial pressure back. And this is so-called time reversal equation, and this is kind of the formally in the inverse of the problem. So this is just to show the contrast between the adjoint, which is the source problem, to the time reverse equation, which enforces the data as hardwired constraints. Okay, so this is at given points, while the source term is more additive in nature. Okay, so these two things are not the same. So this is just to point out. And so the time reversal is good, first of all, if you fulfill those conditions. And so the major advantage of the time reversal type of approaches are to restore the amplitudes to partially observed singularities. And these are the kind of iterative time reversal, non-series type of approaches. So in contrast, when we have very sparsely sampled data, so the most of the singularity is actually not observed at all, so there's no pressure to restore. So in this case, we are interested in using variational formulation and filling in this information that we haven't sampled because we have sparsely sampled data using some kind of regularization. And so in this case, it makes more sense to use variational approaches, and the adjoint operator is of course a part of the gradient, so we will need this inside of those approaches. This adjoint operator can be defined rigorously for partially sampled data, and yeah, so it's for a partially sampled operator, you have a rigorously defined adjoint. So this kind of the details of our view on this, we are not the only ones who have been working on this adjoint. I've included references on the previous slide, but just to highlight the difference between the paper here and then the functional approach taken here is that in the other paper, we assume actually that the detectors are not pointwise but small volumes. So here we really work with points for the forward solver that they are going to try to promote. And the difference is really that everything works exactly as in the paper, but all the integrals have to be evaluated in the sense of the definition of the Green's function. Okay, so why rays for acoustic? So when you think of photoacoustic, you usually think of full wave inversion, and there is good reasons to do this, but there are also good reasons to think about rays. So the first reason is that you have sparse data. Then of course the full wave solvers cannot take advantage of that, and then sparse data are getting more and more ubiquitous in various applications. So when we want to do something fast, we want to do something dynamic, we want to do something in the region of interest rather than everywhere, or we are otherwise kind of doing something not exactly completely, and I can't do it, can sample perfectly, and so on. So the as I probably already said, so the full wave solvers, they would not be able to take advantage of the sparse sensors. So if the data is sampled sparsely or is sampled densely, they all the same to them. So the other reason to look at rays is that we are in the realm of tomography, and in tomography, ray methods have been kind of the beginning of the algebraic reconstruction, really. I would say that the reason for that is probably very contrary to the goal of the Excalibur, because it is more like the kilo-scale computations or something like that that cause people actually to look at single rays rather than the full forward operator. But it is this view is still valid in case if you have huge problems, and also it's immediately valid in case if you have only sparse sampling. And it also is redeemed by the advent of the stochastic gradient type of methods that are so popular in machine learning nowadays. So we are seeing we are seeing these partial forward operators coming in from this direction as well. So the rays are massively parallel. They can be executed on GPUs which are tailor-made for rays, though not exactly the type of rays I'm going to talk about. And so the one application that I may be the most excited about is to combine photoacoustic and ultrasound reconstruction. In ultrasound, ray approximations to wave solutions have been used routinely. However, they are in part we go a little bit, we have a bit more structure to it, which I hope to convey in the future slides. But so there is an interesting fact, of course, relatively easy to see, that once the ultrasound tomography, and if you have ultrasound tomography together with photoacoustic one, the ultrasound tomography has converged, the speed of sound has converged, but the ray trajectories that you have from the ultrasound are exactly the ray trajectories that I am using in part. Okay. Right. So so let me quickly explain how you get ray solutions to wave equations. So this is based on making the following WKB ansatz, substituting this into wave equation and equating the terms of the significant order. So when you do that, in terms of omega, which is the frequency, so this is an asymptotic approximation, the limit of the frequency going to infinity. And so the two kind of significant terms give rise to two equations. One is the iconal equation, one is the transport equation. They are corresponding versions in the frequency domain. And in fact, for our application, we actually solved the frequency domain equations because our time dependence is fully implicit. So only the time dependence is only in the trajectory being dependent on time. So, but I don't want to kind of go into many details. So there is kind of these two type of equations, and now those are now sourced by the method of characteristics, and so this is done by looking at this dispersion relation introduced by this iconal equation here, and computing solving the corresponding Hamiltonian for this dispersion relation here. So this is just a system of equations here that you just that you have to solve, that you have to integrate. It is of course in a higher dimension because it is now in phase space where you have the direction of the ray, and then you have the parameter along the ray. Okay, so when solving this Hamiltonian system, you obtain the trajectories, and okay, so each of those trajectories have some initial data, and that this initial data corresponds to the initial point of the ray and the direction in which the ray was shot. Okay, so when we have the trajectory, so the phase along the trajectories in our case is just the propagation time, and the amplitude along the trajectory can be easily obtained solving this transport equation, and has this analytic form here where the eta is the inverse of the speed of sound, and q is a determinant of the Jacobian, which is a derivative of the trajectory with respect to the initial data. You can think of this Jacobian as an inverse density of the rays. So we have this kind of coefficient here that we can evaluate. So this Q has to be computed, and there are different ways of computing it. You can either solve the ODE system that comes with it, or you can do proximal ray approximation. We actually tend to do the latter. So you can evaluate this density of the rays along the ray trajectories. Okay, so once we obtain those rays, so we now do the following setup. So we take the sensor location x0 and we shoot the rays so in all the directions so that they cover the whole domain omega here, and we trace them until they have left this this domain, and so that they cover the entire domain. So if these rays are nice, so it means if we have if they don't intersect or interact in another ways, essentially if they don't form caustics, then we have and if they cover the whole domain without shadow regions and so on. So we have actually a coordinate system that we obtain in this way. Okay, so we have a coordinate system that is parameterized by the start at x0, and is parameterized by the direction of the ray, and is parameterized by the coordinate dimension along the ray. So if these rays are not a coordinate system for the reasons outlined before, like caustics, for example, they are still a useful parameterization of the domain, and it's just going to use it. So this is an example. So if you have if you take 2D and you generate yourself this speed of sound, which you recognize as a fixed function from MATLAB, and it oscillates around this 1,500 and something here at about plus minus 10%. And so you trace rays from a few locations with respect to the speed of sound. So this is kind of what you see when you trace them from here. This is what you see when you trace them from here. This maybe the most interesting one. When you trace them from here, you can start to see something happening here that actually interferes with my coordinate system assumptions. And then this is, of course, also a kind of sparsely sampled region. So this is pushing it in terms of the variation of in the soft tissue, and in photoacoustic applications, we are most interested in soft tissue. Okay, so okay, so we have this coordinate system now. So what we're going to do, we are just going to take the Green's integral formulation for the solution of the initial value problem. This is my starting point. And I'm just going to try to compute so this formula here gives me a solution at my point x0, which is my sensor over time. So this contributes to my forward data. Okay, so this is part of my forward operator. If I do it for every sensor, I have evaluated my forward operator. So I'm going to take this Green's integral, and I'm going to change the coordinates to this ray-based coordinates that are just introduced at the point at the sensor x0. So this is the change of the coordinates. Yeah, I just made all the substitutions, and then I have, because of the change of coordinates, of course, have the determinant of the Jacobian coming in, and it is nothing else than the Jacobian that we introduced previously. It's exactly the same Jacobian, and that's why you can. This is connected, of course, to the fact that you can think of this Jacobian as the inverse density of the rays. Okay, so this is my new integral here, and I'm integrating over the kind of all directions that cover the domain, and I am integrating for time t long enough so that the rays cover the domain entirely. Okay, so now I can do a couple of Green's function invariances, and I can recompute we can rewrite the Green's function I had on the previous slide with the Green's function with the source at the sensor. This is just purely using the time reversal and shift invariances, maybe changing some the variables under the integration to the -1, something like that. So those very simple elemental calculations that we do, and then kind of we rewrite this integral in this way. And now we have, so the key point is that I've rewritten the Green's function with the source at the sensor. And now I'm going to make an assumption that this Green's function close to the sensor, the speed of sound is constant, and I can approximate this Green's function, yeah, this one, close to the sensor by the homogeneous Green's function in this space for the speed of sound that is at x0. Okay, so in the neighborhood of x0 this holds, and now I'm going to use the amplitude formula from the ray approximation to approximate my Green's function all along the ray, starting from this initial point and x0. Okay, so this is what I can do with the rays, and give me exactly this, how the amplitude from a given point is going to decrease along the rays. So after I change the coordinates to the ray system, I can now use this. I can use the ray formulas to compute the amplitude to compute the Green's function. Along the ray. So this is what I'm doing, and there is also there is some synchronization coming in here that comes from there's some shift in time of propagation that has to do with that it takes the finite time to propagate along the ray, and then this new coefficient comes exactly from my ray amplitude coefficients that I had before. You remember I had A and A0, so this was the coefficient between the two. And this is exactly what is going to be applied to this G0 to produce my unknown Green's function G. Okay, so now I have this this formula here that is expressed in terms of these quantities. I can calculate them all. So I can calculate the speed of sound. I have to reinterpolate the speed of sound at along the ray trajectory, so or the inverse speed of sound along the ray trajectories. My Q's, which is the determinant, something that I evaluate along the rays anyway. So I have this available. I have to interpolate my initial pressure along the ray trajectory. So this all can be done. So I have this integration here, and this corresponds to evaluating to integrating along the points that are equitemporal surfaces. So which is what you do in paths. You kind of, your sensors integrate the signals that come from at the same time. So the deriver that detects at the same time. So this is exactly what this part of the integral is doing. And now I have this derivative of the homogeneous Green's function that in the free space that I convolve with. Okay, so this is my forward operator in ray form. So what is different to the kind of to the classical ray approximation is that we are actually going through this Green's formula, and so we can express all these quantities that are nice in photoacoustic, that they integrate, how the integration is happening very naturally. And also you can argue that we have a higher order of asymptotic convergence, if this interests anyone, because of the assumptions on the decay of the initial pressure, on the Fourier coefficients of the initial pressure. Okay, so the without going into the adjoint, because it is exactly the same idea. So I start now with the Green's integral formula for the solution of the source problem, which is this one here. And now I'm going to change the coordinates again to this same coordinate system. And sorry that this keeps happening. And I'm changing the coordinates again to the Green. I evaluate all sorts of integrals to all sorts of invariances on the Green's function, do exactly the same type of approximation that I have done before, and I get a adjoint operator for one single source in this particular form here, which sorry, I get the, so this is not yet the approximated function. So this is just a reformulation, and then after I have made the approximation, I get this for a single center, I get this adjoint operator in this form. So this is after I have done the approximation of all the Green's function invariances. So again, it looks like a kind of convolutional integral of the derivative of the homogeneous Green's function here, and all the other quantities as something that I can compute. To obtain the whole adjoint, we have to sum up the contributions from all sensors, so that this is just in every point in space X, we are going to sum up all these contributions. So I should point out that both those formulations, the forward and the adjoint, use exactly the same ray system. So the rays are traced once. So they are the rays that you trace from the sensor to cover the whole domain. They are used in both problems, in the forward and the adjoint problem. And they are used, so the natural point of view is actually the adjoint problem when you backpropagate from the sensor back into the domain, because this is where you actually trace the rays into the domain. So this is the natural one. And we use the same ray system, and we can compute all the quantities, all the reverse quantities that we need along the way, reversed rays and some reverse densities and things like that. And all this can be computed from the forward quantity, so to speak. So there is just one evaluation, one calculation of this Hamiltonian system and of this densities, ray densities, and or if you wish, the Jacobian determinants. So yeah. Okay. So let me show you some simulations. So we have this phantom here. It is 3D phantom. What you are looking here. You are looking at the maximum intensity projections, looking looking at this phantom from the top, and looking at this phantom from two other sides. Typically in photoacoustic, we have the squashed volume, so it means that the depth is smaller than the actual size. This will do, of course, with the penetration of light. So we generate ourselves a sound speed that is 10 plus minus 10% variation on this kind of 1580, which it would be meter a second, which would be kind of representative value for the soft tissue. And this is a very non-representative, potentially smoothly generated sound speed variation. But yeah. Okay, so we have a domain, and the domain is of the depth 80, and then the resolution of the sensors, or resolution in this plane here is 240 by 240. And we actually going to place sensors at every second point in the grid, corresponding to 120 times 120 sensor elements in this plane here on top of the volume. It takes 485 steps for the wave to pass through the domain, and so this is kind of the so our grid has 120 by 120 sensors. So if we cross section through this grid and actually drop every second sensor, so this would correspond to the 25% subsampling of the sensor array. So this is the type of the data that we are going to see. So it looks a little bit digital, because it's already, it's already subsampled in a sense. Okay, so this is the back projection of this data. So if you just compute the adjoint problem with the subsampled sensors only, so this is what you get. And then so you can see that there is kind of quite a lot of noise, and there is kind of a lot of shadow here between the detector and the actual structure. Okay, so that is the adjoint. So there is some work to do to do the reconstruction. We cannot just compute the adjoint and be done with it, essentially. So we are going to use variational methods. So our formulation is going to be a very simple one. So we are going to use L2 data fidelity term and the total variation regularization. U is our initial pressure that we wish to reconstruct. G is our data, so this is in line with the notation. P is the forward operator, photoacoustic forward operator. So this is the variational formulation that we wish to solve. And just going to apply a handful of methods to it, such as forward-backward splitting and primal dual hybrid gradient, which are kind of converge optimization methods, and the stochastic counterparts thereof, if you wish. So stochastic forward-backward is kind of a stochastic gradient descent, and then and stochastic primal dual hybrid gradient method. So this is the one that I'm particularly interested in. So just to make the notation fit the notation in the method. So the data fidelity term is abbreviated with this F functional here. G is the regularization term. So this is the general setting, and we have our forward operator that is capable of being split into the partial operators pi, so that if you stack them on top, so this is like taking the rows of the matrix, for example, for the linear operator. So you can stack them on top. In this case, the adjoint of this because we have a linear operator. This is linear setup. Then the adjoint can be for such a aggregated operator or partial operator stuck on top is of course expressed in this way here. And yeah, so our data, our quadratic penalty data term is separable in the same way as the forward operator is separable, and then we have this this regularization functional G. So the primal dual hybrid type hybrid gradient methods, they use the saddle point formulation that changes rewrites the problem here in this saddle point using the convex conjugate of F here. And for this partial operator structure, this term here splits into the sum. Okay, so this I is under the sum here. So all those terms can be executed as a sum. So based on this observation, Matthias and collaborators, they have proposed that a generalization or extension of the primal dual hybrid gradient scheme originally proposed by Chambolle and Hock, and to the stochastic setting, which is it is the kind of very close to the classical primal dual hybrid gradient, meaning that it capitalizes on this saddle point structure, and it alternates the steps of the steps of the primal descent and then do primal descent and then dual ascent here. But now we do this every time for the selection of the indices for a partial forward operator. Okay. So there is a lot of assumptions that has to be made, so that that you choose all the measurements are definitely are chosen with non-zero probability, and there are some conditions on the step sizes that are kind of inherited from the primal dual hybrid gradient setup. But what is interesting here is that in each of the iterations we apply only partial forward and partial adjoint operators, yeah, but the aggregation that is happening here has the effect that at the end you have the full adjoint applied, and this affects the variance reduction in this scheme, which is nice. So this method is essentially tailor-made for the ray operator, because ray operator allows you to execute acoustic in terms of partial operators. So full wave inversion has just one, runs the whole forward operator. There is no splitting of the source. So if you use the ray abstraction, every sensor produces, for every sensor we have a partial forward operator, and we can use it in conjunction with this method to compute the result. Okay, so this slide is actually really only to show that to prove that worked. Okay, what is actually important, there is virtually no differences I can see in those images.
Marta, 5 more minutes.
Yeah, I will be done by then. There is, this another thing that is important is the number of iterations here. So the forward backward to achieve this wonderful state in which all these methods found themselves, is this forward backward method needs 35 iterations, and then the primal dual hybrid gradient needs 79 iterations. With the stochastic forward backward needs 100 iterations, but this has to be taken with a grain of salt, which will be visible on this next slide. And here we have the stochastic primal dual hybrid gradient that only needs 14 epochs to achieve it. So we have essentially have a reduction of factor 4 between these two in terms of operations of the application of the forward operator if you see it as a whole. Okay, so this is a bit more, this slide is a bit more, is better visualization of what is going on. So we have these four methods, and then you can see there is a kind of, in terms of the objective, of the relative distance of the objective function, this is the measure that is used to visualize the convergence here. So we have the Primal dual hybrid gradient, which is the magenta one, and then we have the forward backward, which is the red one, and then we have stochastic gradient descent, which is the green one, and the cyan is the stochastic version of the Primal dual. So what you can see is the stochastic methods are converging quicker. So now the Primal dual hybrid gradient is actually going down to the stopping threshold, while we get the stagnation in the stochastic gradient descent method. There is no variance reduction in this method, and it's done with the constant with the fixed step size. So it's expected. Okay, so that is just here basically for the comparison purposes. So in terms of the signal to noise ratio, you can see that the picture is essentially the same. So the Primal dual hybrid gradient is the stochastic version thereof, sorry, comes on top, and we achieved the same result much earlier. And then you can see that they kind of in this measure the stochastic gradient descent kind of did not match the performance of the other methods. Okay. So this is the simulated data, and now the very last point I would like to make is the real data. So we have the same geometrical setup, and we have with the real data now, and then the estimated speed of sound, something that you do kind of try to fit what would be the assuming constant speed of sound in the volume. What would be if you don't have a ultrasound CT hooked up to it, so that's the best what you can do. So you estimate the speed of sound to be about this. So the subsample data now looks like that, and you can now see that the beautiful kind of looking hyperbolic waves are not anymore so visible. There's a lot of stuff going on. So this is some kind of faulty detectors or something like that going on. So there's the real data. There's a cross section for the real data, and if you take this data, which corresponds to the slice with the subsample data, and back projected, this is what you get. So you can argue that you can see something here, but there's a lot of noise, and the fine structures disappear, which you can appreciate if you take the full data and run a variational solver to something that we consider convergence, which is depicted here. Okay, so if I was able to move between these two slides easier, yeah, then you can see the difference. Okay, so the fine structures come in, and then the fine structures come in, and then the noise goes down. Okay, so this is now when you run this set of these four methods on this data, and this is the results that you get. So essentially, the results, again, the most important part is really the number here. So the 44 iterations for the forward backwards, 56 for the Primal dual hybrid gradient, and then 14 for the stochastic version. So there's a slightly less difference in terms of the number of the iterations here. That for the simulated data, I guess that's live. However, what is interesting in this plot, now you can see that if you remember the green and the blue lines, the cyan lines were coming quite together until the stochastic gradient descent essentially stagnated. So now you can really see that the Primal dual version, stochastic version, is actually doing better than the simple forward backward splitting. So you actually really, so my hypothesis is that this is because of the noise and the imperfections in the data. So you really see the effort that you put in the dual. Okay, so the yeah, so that's the convergence picture. So that the non-stochastic methods are the two here, and then the Primal dual hybrid gradient actually is slower than the standard forward backward, apparently. So you don't see this property in the non-stochastic situation, which is interesting. Okay, so this is corroborated essentially in the peak signal to noise ratio. So this method just here reached the convergence threshold. So that's so those here apparently and now can achieve higher signal to noise P signal to noise ratio. So the question is if this is a question of the measure or if this is a question of the quality. You can judge for yourself. So what you can see is that the spine structures in all of those images essentially to certain degree so are visible, and the noise is to certain degree gone. It's not perfect, but it is what it is. Okay, so this is what I had to say. I hope I didn't overrun. And then so there are some papers on archive and in preparations that if you I know it is in preparation you cannot really look at, but you can look into the thesis of Kiko, which is available on the UCL Discovery, or email me by any means if you have any interest in this type of stuff. And the last thing I would like to put to everyone is that I have a PhD available now to work on Gaussian beam for ultrasound CT. And so I am looking for numerical analyst, scientific computing, and inverse problem kind of person. I mean, they don't have to do a background, but they should be able to learn those things and have excitement for those things. And what I can say that the maths under this ideas is really, really cool. So it will be really fun to work on it. And I'm looking for someone to share this fun with me on this Gauss project. And if you could spread the word, I would be very, very grateful. So please let anyone contact me who is interested. Thank you very much.